I am delighted to have Cynthia Huang visiting from Monash University from the Department of Econometrics and Business Statistics. And she's here visiting the InfoVis group, and she's been here for a couple months. She'll be here for about another 6 to 8 weeks till the end of November. So if folks want to talk to her while she's here. And with that, I would like to take away visualizing category graphs for data harmonization.
Thank you, Tamara. First up, thank you, Tamara and Francis, for hosting me on this visit, and for the rest of the InfoVis group for welcoming me into the group. So today I'm going to be talking about, well, I'm going to introduce myself a little bit, and then I'm going to talk about a workshop paper actually that I presented first last October, where Francis and I met at, I believe is in Melbourne of last year. And I might give you a bit of background of how I, as an economist, an econometrician, applied statistician, data scientist, ended up visiting the InfoVis group. So a bit about me. I'm a final year PhD candidate supervised by Professor Rob Heinemann in Econometrics and Business Statistics in the NumBat group, which is the non-uniform Monash business analytics team. NumBats are also a very cute marsupial animal. And my two kind of co-supervisors, firstly, Professor Simon Angus in Econometrics, and also a co-founder of the Soda Laboratories, where I worked as a research assistant prior to starting a kind of PhD journey. The lab specializes in adapting alternative data for social science insights. And then finally, Dr. Sarah Goodwin from the Department of Human-Centered Computing at Monash, affiliated with the Embodied Visualization group, who work on immersive technologies for data analysis. So as you can see, I have a very interdisciplinary supervision team. I also have, in my past, training as an economist. So that was kind of my undergrad. And I started kind of working with data, curating data sets for economics research, which is how I got into data science and the research that I'm currently doing now. So my thesis title for submission in about 4 months is Unified Statistical Principles and Computational Tools for Data Harmonization and Provenance. It is a very broad topic, but I'm predominantly interested in data wrangling and provenance approaches that incorporate statistical and computational workflow considerations. In addition to that, I'm very interested through my work also at Soda Labs in kind of statistically sound, well-documented and low-friction adaptation of alternative data for empirical research. So in particular, I've been working with a group of public health researchers on adapting web scrape retail prices for kind of policy analysis. Also, I'm here in the InfoVis group working with Tamara and Francis on provenance concepts across different domains in the data sciences. So in particular, in statistics and in kind of computer science domains, and we'll be developing that over the rest of my time here. But today I'm going to be talking about the kind of first chapter, or kind of first big project of my thesis, which is Unified Framework for Recoding and Redistributing Numeric Data Between Categories. It's a bit of a mouthful, and with examples it will become more clear what exactly the task I'm talking about is. So without further ado, I'm going to move into the kind of bulk of the talk, which is talking about these category recodings and redistributions. So as a bit of an overview, the talk is roughly going to be broken up into kind of domain context, a bit around the task abstraction that I came up with, and then rather than kind of a large contribution in coding design, this talk is a little bit of a pitch for collaborators and for ideas from people who know more about visualization and kind of implementing these things than I do. So to start with, the domain context that I am working with is the definition or selecting of mappings between classifications and taxonomies. This occurs in a wide range of fields, from ecology, so thinking about like plant and animal kind of taxonomies, but the context in which I first encountered it and first had to work with it is in kind of official statistics from different countries. I'll give a detailed example in a second. The kind of task abstraction or task that we're working with is kind of implementing and validating mappings on a particular set of data to kind of transform them, say, from one classification standard to another. And then the encoding kind of design task is thinking about how do you actually document and potentially analyze the mappings of this data. So the specific task is ex post harmonization, and this is kind of the data harmonization part of the title. Data harmonization is a very kind of broad term that generally means doing something to data and then mixing it together. Ex post harmonization is kind of one of the words kind of commonly used, particularly in social sciences, to refer to procedures applied to already collected data to improve the comparability, right? And so in this like little stylized example, you can think about having a data set of interest kind of collected in Australia and in the US, and they use kind of different categorizations. And if you want to kind of do a cross-country analysis between, say, Australia and the US, you need to transform at least one of these data sets before you can merge them, right? So you have this kind of individual data wrangling or data cleaning step for Australian data and US data that may be kind of performed by a national statistical organization, say like the Bureau of Statistics. And then as a researcher, looking to say compare things across multiple countries, you then often need to do kind of this additional pre-processing or transformation on these specific data sets before you can merge them together. So to give you guys a kind of concrete example, we can think about occupation code mappings. So if you've ever filled out a census, they kind of ask you questions about your occupation, and there's actually like often an official list of occupation codes that people's answers, so you might write like a free text answer, and then there's like a set of codes that everyone's answers get coded to. So in Australia, this is called the Australian-New Zealand Standard Classification of Occupations. I may have that wrong. And the 22 on the end actually refers to the version. So as jobs kind of come and go over time, the like official standard for classifying jobs also changes over time. So even within a given country, if you're trying to analyze data across time, you may have to deal with this kind of harmonization task. But here I've kind of included an example of a lookup table between the Australian standard and the international standard classification of occupations. Right? And so you can see that clearly there isn't exactly a kind of one-to-one match, because you've got 6 codes on the left-hand side and 5 codes on left-hand side and then the right-hand side. And so the type of data to think about here is often kind of aggregated counts, right? So you do an individual survey, and then there's some sort of aggregation. These are often the kind of resolution or granularity that these statistics are released to kind of researchers. You can also get access to kind of more granular responses, but that's usually restricted. So then keeping in mind that you've got here like 2 different sets of codes, there is some mapping that's sort of kind of definitional or semantic between, you know, the different codes. But in addition to that, when you're thinking about recoding the counts, you actually have to think about how to redistribute, or potentially think about how to redistribute the actual numeric count data, right? So if you're thinking about straight translation, so like teacher to, you know, teacher in say Chinese or whatever it is, that's a kind of like one-to-one mapping. And so then the count stays the same. But if you have a mapping where, say, you've got occupation A that goes to 3 different occupations, you then actually have to think about what are you going to do with those counts, right? And there's a bunch of different ways that you could deal with that, including picking like the best match or using some reference information to kind of redistribute that data. So the possible relations, you can have a one-to-one kind of unique, which you can think about just as a renaming or recoding. You could have like kind of one-to-one shared link, and one-to-one shared being kind of this bottom here, where the numeric transformation is still kind of the source value kind of goes over one-to-one, but then it gets aggregated up. And then finally, the more tricky kind of transformation is this redistribution, right? So these top links where you maybe have kind of many to one, one to many or many to many kind of relations. Okay, so then given you have designed or decided how to do that kind of redistribution, how should you implement it, right? So this is like a real kind of task that I was given as a research assistant in trade, working with a trade economist. She had a kind of correspondence table and some idea of how she wanted to redistribute these counts, and then gave that to me, and it was my job to implement it. And so looking around, basically what you have is a lot of bespoke implementations of this type of recoding and redistribution. Usually it can be something like a if-then statement. If you started in category A, then assign X percentage to category B, category C, and so on and so forth. In order to validate that you've done the transformation correctly, you can think about some sort of like input-output checks, right? And so one really basic one is that before and after the transformation, the totals should still sum up to the same amount. So like if I had surveyed 100 workers after the transformation, even if I give their jobs, different names, or I redistribute them to different jobs, I should still have 100 people on the other side. So what are some of the so as you can tell, this is sort of ad hoc, and I'll actually show, or maybe you can imagine, this is actually not an airtight way of checking that you've done the transformation correctly, because there's actually multiple ways in which you could, say, aggregate a certain set of numbers into another total, right? So there's not a unique mapping between these two kind of inputs and outputs. So this is just a bit of an example. This is from a status script that's kind of commonly cited in trade economics for doing concordance between a bunch of different like product classification standards, and it's 800 lines, and it reads like this for each, for every, for do all this stuff. And so you can imagine most people really just take that and go with it. And so in kind of seminars and things, when people suggest like, well, have you thought about mapping it in a different way, using a different set of weights to transform the data? Usually the response is, that's a great idea and we'll do it if we have time. But being the person who's implemented this and taken like multiple months actually to do this type of data set cleaning, it's really infeasible to try different mappings the way that we currently work. Okay, so this is kind of the problem set up. Now I'm going to talk through the kind of conceptual solution that I came up with, and I promise eventually we'll get to where like the visualization piece and kind of interaction piece could come in. But basically, I looked at this task and thought, well, could we do it differently? And so my proposed solution is sort of a kind of framework-based approach, which I'm calling the crossmaps framework. The crossmaps name comes from an adaptation of crosswalks. So if you know about kind of one-to-one remappings, often you'll have like a crosswalk lookup table, and then maps kind of refers to the mapping. But the kind of crux of this idea is that you could use graphs. Well, you can use the equivalent representations of graphs as both matrices and tables to kind of translate between different representations of this task. And so, as I showed you before, it's actually quite common in the social sciences to use graph diagrams to illustrate the type of transformation that you're doing. But then once you have that illustration, the actual task of implementing it goes into this bespoke script that is 800 lines long or whatever it is. And so the core idea that I write about in this kind of preprint paper, a unified statistical computational framework for ex post harmonization of aggregate statistics, is that you can actually translate between the graph, matrix, and list representations under this single unified definition of a crossmap, and each of these representations gives you different advantages and disadvantages, right? And so, in the interest of time, I'm not going to go through like in minute detail what each of these things are, but you can have as I kind of mentioned before, you've got graphs for documentation, right? So this is really where you could have like just the visualization, interaction. It's clearly a very good format for communicating what the mapping actually is, right? Because you can see it, you can say, okay, this particular category was redistributed to another category, right? Like that's visually on screen for you. The matrix multiplication representation is a little bit more subtle, and it really comes a lot from the fact that a lot of statistical procedures, data transformation and estimation procedures, so linear regression, all of these sort of like statistical procedures all have a kind of linear algebra representation. And the niceness about this is that these representations give you certain validation properties, right? They say certain things like, if you're trying to translate from, say, data that's in one classification, the mapping that you use should have the same dimensions, right? So you should have instructions for every single category in the original data. So if I have, say, 10 occupations in my original data, I need instructions for every single one of those, and that requirement translates into a kind of matrix conformability condition. The last insight is that you can then use this edge list representation for efficiency, but the other neat thing is that there is a one-to-one translation between kind of matrix multiplication and representations as SQL queries. And so you can do things not only thinking about kind of dimension size conformability, you can actually look up and make sure that you've got instructions, say, for every single category in your original data, right? So you have these kind of three representations. I have both a paper on kind of describing in a little bit more detail exactly how these definitions work, so defining a crossmap in each of these encodings, and the various implications, right? So we can then think about things like checking transformation logic, just by checking that for a given category, all the links that go out from it, the weights on those sum up to 1, right? And that just says that if I've got, let's say, 100 in this category, once I've distributed all of those workers to their new jobs, the sum of those should always sum up to 100%. Right? So you can never have, the appearance or disappearance of a person. Okay, so then if you're interested in those kind of specifics, I can talk a bit more about that offline. But I wanted to move on now to kind of further discussion and like linking it back a little bit to kind of visual encoding design and kind of other implications. So kind of broadly, the way I think about this work is that it starts very much at a domain problem, which is ex post harmonization. And kind of associated with this are actually a lot of calls for like a standardized toolkit for this, a standardized way of documenting ex post harmonization, often because we're thinking about transforming data from 50 or 60 different data sources and combining them together. Having a systematic way to actually track all of those transformations is incredibly valuable. And that's where the kind of bulk of my work has been, is just thinking through that task abstraction and the representation. Like, rather than having these kind of very, very long scripts, if we think about the script as actually being a representation of this graph that we could actually store also as a table, we can then think about the mapping function just as a collection of tables, and they have these kind of nice properties that make them, analyzable in ways that are kind of much easier to understand than, say, analyzing a script. So what does this mean in terms of research opportunities? So this niceness of being able to manage lots of cross maps means that in statistics, at least, you can think about actually playing around with different mappings, right? Because you now have this object that separates the mapping logic from the actual implementation of the mapping. You can use that object to kind of swap in and swap out different mappings. This allows us to do things like sensitivity and robustness analysis. There's this concept of kind of stability that's kind of being developed in statistics around how stable are downstream kind of statistical results to different choices in the pre-processing stage, and having this kind of modular approach and modular abstraction for applying this kind of complex transformation allows us to think about running that type of analysis, right? Because instead of writing a new script for every mapping that you're trying, you just write a new graph. And but kind of over into, I guess, more data science, CSE space, and I'm not of this area, and so this may be in or out, but definitely the design of kind of documentation and auditing of these types of data transformation workflows, that's an opportunity as well. I think of most interest to me is kind of interactive tools, like how can you actually make it easier for people to author, audit, and apply these types of transformations. There are some subtleties around like floating point representation. So if you think about taking a group of, say, 100 teachers and dividing them into, say, like principals and like assistant principals or whatever it is, if you have a weighting of, say, like 0.3 and 0.7 as the weights versus like a kind of symbolic representation of that, depending on how you actually apply the transformation, you kind of accumulate these little floating point errors over time, which can mean that the totals don't actually line up after you do the transformation. And then lastly, of course, kind of visual encoding, like what makes sense for thinking about how to visualize, let's say, a set of 100 or 200 or 300 categories going into another set of 300-400 categories, right? Like, what is the best way to kind of encode that information and make that accessible to people? So I worked on a kind of prototype implementation in R. I don't necessarily think that R is the best, was the best place to do this. It's just that's what I'm familiar with as a kind of someone coming out from, I guess, applied statistics. And so it has, the current package has like two features: a data structure for the crossmap, and this kind of diagnose as a crossmap function basically checks for all of these like mapping constraints, right? So there are certain characteristics of the graph, for example, that weights should sum to 1 and all of this. It checks for all of those properties, and before you actually transform the data, it can say, would this be a valid transformation, right? Like you can kind of check before applying in a kind of static way, does the transformation make sense? Then there are these kind of like batch and apply operations to actually transform data, and this is where you take in the mapping and the data and like actually transform them together, right? And there's also a diagnose operation there, because you need to think about, well, if I give you a data set that has, let's say, 500 categories, and you give me a cross map that only provides instructions for 100 categories, I shouldn't be allowed to take that transformation and apply it to my data, right? And so this is the type of kind of like diagnostic flags. But really, I'm missing a lot of things that would make this framework actually useful or kind of applicable to a lot of people. I don't currently have implementations of like graph or matrix classes. I haven't implemented the symbolic fractional weights yet. The kind of other upshot of this abstraction is that you can think about extracting the logic. So if you remember that 800-line script, the kind of formalization of this task allows you to do things like pass in kind of manipulated data that allows you to then trace what would be happening to data attached to a particular category, and you can kind of reconstruct the mapping that way. You can actually extract it. There's also this question of like, okay, so you go from having this like one collection of scripts to just having lots and lots of graphs. Like what makes sense for thinking about workflows where instead of defining functions, you're defining lots of graphs and then thinking about applying them to your data. And then lastly, there's kind of other things you could think about in terms of analyzing the properties of a mapping to say, if a mapping only has one-to-one links, we know that this is just a renaming and it's not really imputing or creating any new data. But if you have a mapping that has lots of many-to-many links, then you're really creating new data, and it is meaningful actually when thinking about a harmonized data set to distinguish, which case you're working with. Yeah, and then obviously kind of visualization and editing. So in the workshop paper that I presented last year at the Viz Prov workshop, I kind of just proposed a couple of ideas around using visual channels to really highlight kind of key features of a transformation graph, right? And so you can see here, I'm thinking about like which data connected to which occupation codes get split versus don't get split, right? So you've got these like dotted lines, for example, and then that potentially tells the reader that this part of the data set needs more scrutiny, right? Like there's more subjectivity in terms of the creation of the data set at this point. What proportions are used, right? And there might be annotation around like where those proportions came from. And so in the case, say, of like geographic redistribution, so you have like census data and maybe like some election data, when people are trying to merge those two types of data sets, you have to often redistribute, say, votes across kind of census tract boundaries, right? And so there's various ways in which these weights can be created, and it's important to kind of document how that happens as well. And then, of course, like what's the composition of the transformed data? And so this is like, I think, a pretty straightforward like use case for people like you who work on like tools and graphs and things. There's obviously a lot of opportunity in terms of just like the provenance documentation part of it, right? You've got this object, and then you can think about like, how would you summarize the graph? How could you lay out the graph? Interactivity, I think, is a really interesting opportunity as well. But the main problem, I mean, I've been grappling with, so it took me quite a lot of time to actually create these graphics using like ggplot extension packages, is that like it's just incredibly tedious, and even the layout of like the nodes and the link crossings is like should be more straightforward. I understand that this is basically a solved problem in terms of like layout research, but I think there's a real maybe. But in any case, this is quite a different style, I think, of graph visualizations and say like networks, right, where they've got this like high complexity. It's actually highly structured information, but there is still these interesting questions about how they should be laid out, whether you would collapse things like all of the one-to-one links. Right? The other kind of future work that I'm working on more from a kind of statistics side is using the crossmaps abstraction to really like quantify and communicate and explore the degree of missing data in a transformed data set, right? And so what you can see here on the right-hand side is actually a visualization of output by country year by industry. So if you think about, output for, say, like manufacturing of clothes versus like agriculture, there's like all of these different industries or categories of products that get traded, and then each country collects their records around imports and exports using slightly different product codings, right? And then at an industry level, you can kind of aggregate that up, but if you want to compare industry level patterns across countries, you need to do some sort of harmonization. And so here in the red are kind of not transformed data, and this is data that was already in the international standard before I applied any transformation. And then in blue is country year observations that had to go through some transformation in order to kind of manipulate them into a form that could be kind of joined together, right? And so classically, the way that this workflow would go is that you pass all of these country year observations into the same script, and then it does whatever it does with it. You actually don't have a lot of visibility necessarily about which observations kind of triggered which rules in the transformation process. But with this kind of external object, you can think about then tracking that and kind of quantifying the location of particular imputations in these merged data sets. And then again, as I mentioned before, you can think about then stability analysis, right? And also influential mapping decisions, right? So are there weighting decisions that really make a big difference because they impact a lot of the data that's getting transformed and getting harmonized? So in summary, ex post harmonization is a very complex form of data imputation that often isn't treated actually as the creation of new data. It's really treated just as a data cleaning task. Graph matrix and tabular encodings offer complementary insights and actually maybe for more than just this specific task. So there are a lot of kind of statistically relevant decisions that happen and are kind of implemented in kind of coding script or bespoke coding scripts that maybe could be reimagined in this kind of equivalent encoding way. And then lastly, visualization and interaction design are really needed to realize the potential of this work. I've presented this work now, I think 8 different times to kind of statistics audiences, applied empirical researchers, and everyone's generally very excited about the idea, but it's fine for me to have these kind of mathematical objects and to write down the proofs that these things are equivalent and these properties can hold, but until people can actually see these graphs, interact with them, use them, I think it's very hard for this idea to kind of gain traction in a kind of data science workflow. So on screen, I've got a bunch of related writings, talks, and that's basically it. And yeah, so to reiterate, I'm kind of really looking for design, implementation, ideas, and collaborators. And as Tamara mentioned, I'm here until the end of November. Thank you very much.
Question? Actually, I think I have good news.
Yeah.
Your graphs are bipartite, which is one set mapping to another set, and there's no mappings within the sets.
There can be. So you could think about this multi-year transformation. So you've got occupation codes from say 1990 to 95 to 2000. And so the cool thing though is because there's a matrix representation of this, you can collapse it down to a bipartite graph because you just go matrix. So you've got data, matrix transformation, get new data. And then you put another matrix next to it and another matrix next to it, you can collapse down all those middle matrices. And so, yeah, just like a bipartite, like a k-partite graph, you could just collapse down all of those intermediate.
And then the time dimension becomes exclusively the within set map edge.
Yeah, so you could just kind of skip over, in a sense, the intermediate time steps, right? So it's you went from classification A to classification B to classification C. And this could be across time or even across different standards or whatever. So yeah, I didn't really talk about this in the talk, but it's all kind of consistent in the instruction. There's just a lot of decisions that you can make or need to be made around what do you communicate, when do you collapse, how does that kind of all
right. So it's right. It's not really good news. The good news,
yes,
is that if it's only bipartite, which is the atomic case,
yes,
no more complexity,
yes,
only mapping,
yes,
then it's not solved, but it's a much scoped down problem than
yes,
the general graph we lay upon.
Yes.
That's completely open-ended and
yes,
it unsolved millennium price.
Yes.
The permutation,
yes,
of the 2 columns, that's a bit more. I think you can tackle. I mean, you have tackled it.
Yeah.
But then right, if there's if it's not entirely bipartite,
yes,
then you still need to go into the territory.
As you say, it is the atomic case, right? So it's from classification A to classification B, but there are heaps of real world cases where you then need to go to classification C and classification D. But like the nice thing about thinking about it as a transformation or a kind of computational graph where you're taking data from one classification to another is like you could collapse down those computations. Like there's actually no, currently though, people do just do each step by step because each one of these has a script attached to it, right? So you go from classification A to B.
Is there a scenario where you have and so I'm thinking of it like topologically, like the atomic case is like part-time.
Yeah.
And you make it more complex, but you could go topologically to fully random, which like everything's connected to each other, and that could be a mapping, but it's like really annoying.
Yeah, it would be really annoying, and it's more around like it depends what you're trying to achieve, because you could think about a generalization of this type of bi-type, part-type transformation, and all you have is a category and a value attached to that, and you want to do something with that value. So right now you're like redistributing this value, but you could think about like multiplying it, or like you could do all sorts of different things. And the basic structure of the graph is like you have some indexing set of categories that say any number attached to this category has some transformation applied to it, and then the like label on the link is what that transformation is, right? So there's actually a lot, I mean, of crossover with just like literally computational graphs, right? Where you're like, you like write a function down and then you decompose it into its graph.
So you have, like, think about it in the topology, you have like this, the topological substrate, the atomic case, and then complications of the topology and also complications of the labeling.
Yes.
Which is like all the terms of French.
Yes. Yeah.
So you have this like, and then you can like have orthogonal things that are complex in their own ways.
Yes. Yeah.
Interesting.
But this is like, yeah, I would say like big picture to like kind of going back to like where this work sits for me is like in that task abstraction and representation layer, the idea I'm fundamentally interested in is like, what if instead of bespoke scripts, we use graphs, or we use like representations of graphs to capture some of these more complex representations? Because you could think about a really simple case where you've got missing data, and you could represent that as a graph as well, which you say the two categories are data is there versus data is not, and then only in the case where the data is not, you do something with it. And the really simple case is you fill it with zero. Right? Like, and so this is again like a kind of graph representation of like a very simple like function that people tend to apply. And I think in the simple cases, it doesn't make sense to turn it into a graph. But then as soon as you go into these more complex cases where you're taking data set A, applying some complex transformation to it, turning it into data set B, and then also combining it with a bunch of other transformed data sets, the tractability of the statistical properties of the data sets becomes very, very challenging, let alone the implementation, right? Like this is sort of a side effect. I was mostly interested in it. I mean, there's sort of a back and forth, right? There's like the statistical things that it makes possible, but then also like it makes the workflow less annoying.
Super. Like I now wonder, you know, maybe you have it. The most complex, what like pipeline you've had built, and I would like to see the topology.
Yeah, so I mean, this is sort of where I was getting to with this data set, because you can see here I've got like hundreds of country year observations, right? So each is like, let's say US 2020, and then the data looks like industry A, output X amount, industry B, output Y amount, right? And so here you've got like just thousands of rows of data, right? And each of them is getting transformed in slightly different ways. And so you've got like a bunch of different like distinct graphs that you could like zoom in and look at, like just for the USA or just for the USA in 2020 or whatever. And like all of this kind of at the moment is like one paragraph, not even one paragraph, like 2 sentences in the methods sections of these papers, right? And so, I mean, one of the fundamental reasons I'm like kind of pursuing this idea is like just to scratch that itch of like how stable are some of these like social science insights to just tweaking some of these like decisions a little bit, right? And there's often like multiple sensible ways to map this, especially if you're thinking about historic data. And it seems kind of sad that we can't try at least multiple of these sensible alternatives. And so this is really my attempt to like kind of like from a first principles abstraction perspective, like how do I grapple with all of these possibilities? And then there's a nice link to like visualizing it and analyzing the graph.
But now, because like the atomic case you haven't solved in R, the atomic case.
Yes.
And then this is like the extreme
Yes.
cardinality case, and they look different. Because it's like a different cardinality. Like the amount of things you have to encode are different. But maybe there's like a generalization that works for both.
Yes, this is
I think we'll agree.
exactly what I was hoping to hear tomorrow.
I mean, I think this cries out for some sort of multi-scale representation because it's sort of, you know, the low level details of look, here's a few nodes and here's some links between them. You know, that's not going to scale to when you've got 500 rows in your script about what's going on here. And you can imagine a situation where you might need that level of detail for one or two, but I think the challenge, and we certainly talked about some of this within our group, is how do you give the person any sense of where they might even start looking at the detail? So how do you, I think you're, even just overviewing detail is almost certainly not going to be enough. I think you're going to need multiple levels of representation. And so, and then this gets at, you know, questions like, well, exactly what do they need to know? And, you know, this question. So, you know, you said that your domain situation is ex post harmonization, but then, you know, one layer down from that, it's like, what exactly are the subtasks that people are trying to do here? You know, which bits of the data wrangling pipeline are you trying to support? And so I think there's a lot of sort of, you know, there's a universe of ways you could break this down into what do you actually need to show, and also who. Are you showing the person doing the harmonization? Are you showing the person auditing somebody else's previous harmonization? You know, are you showing someone who just has sort of a casual interest in, hey, what happened here? Those might be very different displays right there.
Yes.
Yes. And so my first guess is that it would be a mistake to instantly dive into the visual encoding of these big and complicated graphs before sort of thinking more at the abstraction level of, you know, for this part of the task, what do they actually need to know? You know, how can they really just look at this like, you know, the equivalent of one row at a time in your table? Or do they want to get some sense of, well, these rows are under control, but these ones maybe need more inspection? You know, so do you want to sort of somehow swap it into good bits and bad bits?
Yeah.
You know, do you have any sort of automated ways that you might do that? You know, because I look at this picture, and if you go, the slide you had a second ago, where you had the sort of Sankey-esque thing, yeah, that one up there, you know, like, those are quite, probably the very lowest level. I think about a tree, like those are the leaves.
Yep.
And then I think in this, the question that's almost always, the tricky bit is, how do you get to the leaf?
Yeah.
Right, what are the interior nodes of that tree, if you thought about it as sort of a navigation cluster hierarchy? And, you know, is there any hope of an overview that shows you what you need to do, or do you have to sort of systematically go through some of these interior nodes and search through them? So I don't have answers, but I think that even as there are graph visual encoding problems that might be here, I think there's a bunch of abstraction level stuff that is going to be really useful to think through before diving too deep into the graph visual encoding stuff. Much as I love graph drawing.
Yeah. So I think I fully agree, and this is sort of like I have been thinking about it, and I think it's maybe a curse that I've given this talk so many times because there are details of this in previous talks. And I think this particular visualization was like one attempt to grapple with that, which is you can imagine like if this were like kind of expandable, like I could go into each of these country year like tiles and look at the actual mapping in that tile. I then would be interested potentially at say like which of the categories did get split, right? So here, this says to me, okay, all of these red tiles, they're fine. Like, this was purely like a rename, right? So it went from like capital A to lowercase a, like who cares, right? But then in these parts of the data set, there was some degree, and this is a binary still, some degree of like many to many types transformation. And so you would think about them like going in and then that displaying some sort of like pop-up or something that allowed you to look into, you know, which of those did get transformed. But then there's also then like the quantification part, which is like, okay, can I just count like the number of split type transformations that's actually happening here? And so I agree in that that's both an abstraction level thing, but I've also found it very instructive to think about the visual interface design that would allow me to explore that type of thing.
And to me, I think one of the most interesting things, and it's a point you make on the slide, is, and so then what if you did sensitivity analysis on, so you try all these alternatives and which bits are stable and which aren't, because then you've got this whole meta level above all that. And but what could be nice is it might seem to make the problem even harder, but maybe it does guide you to something like fairly brutal about just how much you have to simplify in order to have a hope of showing that.
Yeah.
And so it could be an interesting thing to think, you know, what if, imagine for the moment that that problem were solved, and now you're trying to do this sort of stability, sensitivity, robustness analysis one level above that. Does that give you any thoughts about what you would need to show, especially in terms of like latent possibilities? Because, you know, this question of you know, how stable is something, or do you even have coverage of that space? But my first thought is, oh wait, combinatorially speaking, isn't that a giant explosion? So you wouldn't even try to do all possible alternatives. So how did you even decide the domain in which you did your sensitivity analysis? Like, how do you constrain that to a build?
Yes, usually it would be some theory-driven approach to generating the redistribution weights, right? So in terms of like that space is very much domain constrained, right? So like it doesn't make sense to ever have, say, weights that connect like connect teacher, say, to us. There are domain.
So these are semantics that you know that give you some constraints. So, yeah, that makes sense. I asked on Zoom whether any Zoom folks do have questions. I didn't see anything in the chat, but let's give them a moment to see if anyone's.
It's a quick question, because you have a number of, I suppose, rows, and then a target number of rows. Has it ever happened that you get like more rows midway that then collapse down? Like,
Yes.
like a hidden layer?
Yes, yeah, it's entirely possible. And this is sort of why I think the abstraction is so useful for even tracking that, right?
Right,
To say like somewhere in the path, even though it looks like if you collapse it down, maybe it would look like a one-to-one type mapping.
Yeah.
Is there some sort of imputation that's hidden in between? And that actually is quite common. So I did, another thing that happens with these types of classifications is that they have different granularities. So you'll have like a 6-digit occupation code, a 4-digit class, and then a 2-digit, right? So that there are these like kind of general areas and then more specific. And so if you're trying to map between two different classifications, a common thing to do is to do the mapping at, say, the 6-digit level. And you might have to do some splitting or redistributing at the 6-digit level, and then just like to kind of brush over any issues that you think might happen there to re-aggregate up to, say, the 2-digit level to do your analysis, right? And so there's the way that it's dealt with in practice, at least, and I'm actually doing, I'm working on a literature review of this particular kind of harmonization in trade economics, trade and labor economics, to just understand what people's practices are, and they're very much like ad hocly, like informally passed around. And so we're kind of engaged in a bit of a like gray literature search to find out like what are people even doing when faced with this. And I think at least in the CS literature around like data wrangling that I have read, they kind of treat this problem as one that's like, it's too hard. Like you shouldn't, like these two categories don't have, and it's like, well, social scientists are trying to do this anyway. And so like you could either support them to do it better, or, you know, like I feel like there's a really kind of underserved niche here.
Like that is what like the use case of revealing this like hidden deep layer is such a cool like this is the problem and look at what you can reveal like even as a graphical abstract.
Yeah, well, I think even, like this was sort of, when I first produced this, I remember like while working on it, talking to my supervisors and being like, my brain kind of hurts because previously I had one script and I could sort of just explain like, okay, like there's like a bunch of rules for when there's one-to-one, there's a bunch of rules when there's one-to-many, and a bunch of rules for when you're like aggregating. And then I was like, but now I've just exploded one script out into like hundreds of graphs and tables, and like it actually hurts to think about how to track all of this in a meaningful way. Like I know I should have expected this, but it's difficult nonetheless.
Any last questions? All right, I feel like it's difficult nonetheless is a perfect way to end.
Yes.
So thank you so much for the talk. And